So this is going to be a rapid-fire overview of some of the stuff that Khronos is doing relevant to AR. We're all here, hopefully all week, so if you have follow-up questions, please don't hesitate to come and chat. So for those of you who don't know the Khronos Group, we are a standards organization. We have about 120 member companies, everyone from Apple and Google, all the way down through developers and silicon vendors to small startup companies. We have one specific focus in the industry, that we create API standards for hooking silicon into software. So it's the acceleration APIs that you need to run good graphics and compute applications, to drive the sensor, the camera. Every time you need to get down into the hardware, hopefully there's a Khronos API there to making it easy for you to do that in a platform portable way. So we have a bunch of different API standards. The best known ones are OpenGL and OpenGLES and OpenCL, the visual computing APIs available on desktop and mobile. We have some web-related APIs that kind of do relate to the discussion here today. WebGL and soon WebCL for graphics and compute in web browsers. We actually have some APIs that actually aren't APIs, they're format standards. COLLADA is a 3D asset standard for authoring, and GLTF for transmitting 3D data, and I'll talk very briefly about that. But the main focus for today is the vision and input sensor processing APIs. I think they're the ones that are newest and definitely are applicable to augmented reality. So giving an update to you guys as to where we stand on the camera control API, OpenVX for vision acceleration, and stream input for sensor fusion. So it's a really interesting area. Particularly my day job is working at NVIDIA in the mobile space, and I think mobile is kind of the epicenter for innovation in augmented reality, and there are lots of challenges for the software developers, the platform vendors, working to figure out how all the moving pieces come together. So for example, on the input sensor side, the cameras have been kind of fairly, it's been a megapixel race, but other than that, a camera's been a camera. But that's about to change. We're about to have depth cameras, stereo pairs, active illuminators, all kinds of stuff going on in the sensor domain. And how are we going to enable the software community to portably access that kind of new sensor capability? Meanwhile, the silicon vendors are busy innovating, and it's not just CPUs and GPUs anymore. It's DSPs, it's dedicated hardware for doing sensor processing. Perhaps in the future we're going to have a dedicated hardware for 3D sensor processing. Again, how are we going to enable the software community to take advantage of this capability without driving folks crazy? And then last but not least, sensors everywhere, Internet of Things, everything is going to have a sensor, including augmented reality systems. Again, there's potential for chaos in the software development community if every detail of every sensor is exposed straight to the application developer. We have to find the right APIs to enable the developer community in a portable way. So looking down this pipeline, what Khronos is currently working on, we have a camera control API, which is specifically focused on enabling advanced application control of the camera subsystem in a platform portable way. We have OpenVX, which is the newest of the new three. It's for vision acceleration. I'll explain more about VX in a second. We have EGL, which is the often forgotten API standard from Khronos, which is a memory allocation and buffer standard. Lets you allocate memory buffers and have very efficient communication of an image stream, for example, between different APIs. So if you have a camera API and a processing API, you can use EGL streams to hook the two together. And then last but not least, stream input, which is a sensor fusion API, taking input from a bunch of different sensors in a mobile device, plus using the camera as a sensor and bringing them together in a coherent way. So let me give you a little bit more detail on each of these and show how they all hang together. As we've been looking at vision acceleration, one of the key things that's been driving the design of how we are going to expose vision acceleration is power efficiency. In the mobile space, power is the new performance. You can't turn all the silicon on in a modern GPU and keep it on. The phone will melt in about 45 seconds. So the key is what hardware processors do you have in the silicon, and which is the most efficient processor for the task you're trying to do right now. If you go from CPUs to GPUs for vision and image processing, GPUs are more efficient at doing pixel type stuff. The cache coherency is better designed for graphics and imaging. You don't have to move data so far, typically. So you can get a factor of 10 power efficiency going from CPU to GPU. But I think you're going to see another factor of 10 going to dedicated hardware. So it's important that the standards we come up with for vision acceleration aren't just for CPUs, GPUs. No, they have a bigger scope and enable a wider diversity of hardware acceleration. So that's been the background to OpenVX. VX Vision Acceleration. It's a out-of-the-box vision framework. Its design center is low power, real-time, mobile, and embedded vision acceleration. We want to provide portability of vision accelerated software across a wide diversity of hardware, certainly CPUs, GPUs, DSPs, but also the low power dedicated hardware, DSPs and DSP arrays that's going to be in an SoC near you any time now. We want it to be foundational. Lots of the Khronos APIs are foundational. We try to get as close as we can to the silicon to enable the silicon vendors to innovate, but have enough abstraction so we can enable a diversity of different silicon implementations and provide portability to the software community. And OpenVX is no exception. And in that way, it's complementary to OpenCV. I'm sure many of you here are fond of and use OpenCV, but in our experience, lots of people use OpenCV for prototyping, but not many people actually use it for production because, for a number of different reasons, but the main one is it's not that power efficient. It's a memory-to-memory model, and that's the worst thing you can do for your power consumption. So we see OpenVX being quite complementary to OpenCV, VX being provided by the silicon community in a reliable way. OpenCV or applications or other higher-level libraries can be easily ported over OpenVX, and we see OpenCVs continuing to be really useful for prototyping. We are working on an open source implementation of OpenVX. We're planning to finalize this spec before the end of the year. There's already a provisional specification that's available on the Khronos website. So if you want to look with more detail at what's going on in OpenVX, we would really appreciate your feedback right now. It will be a good time to hear what you think. So the key architectural feature of OpenVX that is the enabler for power efficiency. The key difference to OpenCV is that we have the concept of a graph. So you can take the various image processing functions or nodes and up front define how these nodes are going to flow together for the complete vision operation that you want to occur. The fact that the developer expresses a graph up front gives the opportunity to the implementer to optimize the heck out of it. And the optimization will depend on the type of silicon that you have. So if it's a GPU and you have a compiler, you can begin to compress the nodes together. There's a bunch of different ways that you can make this really efficient beyond a single per function call architecture. We have VXU, which is a utility library. So if you're calling OpenCV functions, it's an easy step into using OpenVX. And again, we're using EGL to kind of interop with the other Khronos APIs. So this is the comparison between VX and CV. I mean, OpenCV is a good thing, and we're supportive of CV. We're not trying to compete. We're trying to complement CV. But it's important to realize the differences. CV is an open source project. There is no specification per se, and it's growing, and new functionality is coming all of the time, which actually is a good thing. That's what makes it valuable as a prototyping platform. But if you actually want to come and produce a product and perhaps have silicon vendor agility. OpenVX provides a specification with conformance tests. You know what you're going to get, and it's much more limited in scope, so the silicon vendors can actually implement the whole of the VX spec to give you performance portability across different silicon architectures. One of the other specs that we have, and you can definitely use for vision processing, is OpenCL. And I don't have time to go into details, but OpenCL lets you write C kernels and distribute it across a heterogeneous array of processors. The interesting thing about OpenCL is, as well as being used directly, it's being used increasingly as a foundational layer for higher level frameworks and languages, including Halide, which is not a vision processing library, it's an image processing library, but I think you might well see some compiler-based vision libraries being built on top of OpenCL. So how do CL and VX relate is another table. The key thing about OpenCL is it's a general programming framework. You can write C and soon C++. You can distribute work. It's not specifically aimed at vision processing. It is very tight on its precision requirements. So you have to have IEEE floating point, which is great for some application areas. Perhaps it's overkill for some low-power front-end vision processing. And it's just a programming language, programming framework. So it's not an out-of-the-box vision framework. OpenVX, on the other hand, is specifically designed for vision processing with just the amount of precision that you need for the vision operators that are in the VX library to be consistent. So it is possible to build VX nodes out of OpenCL, and I think that's something that you will see quite a lot in the industry. There's some discussion in the OpenCL working group right now as whether we should have a vision profile for OpenCL where we don't need the full IEEE floating point. So bring these two closer together, the flexibility of OpenCL plus the framework, the power-efficient framework of VX. And there's actually one more set of APIs that you can use for vision processing, just to get it out there. Because I think actually a lot of people will actually use this for commercial reasons, if nothing else. And OpenGL has had compute shaders for a while. So GLSL is the shading language that the graphics community has been using for many years to generate advanced visual effects. Compute shaders generalize graphic shaders, so you can interoperate on any image or buffer that's available to your GPU, and you can implement vision and image processing algorithms just as easily as graphics now. OpenGL-ES is the mobile brother of desktop OpenGL, and the OpenGL-ES 3.1, which was announced back at GDC back in March, just a few weeks ago, now also has compute shaders. So over the next 12 to 18 months, you're going to start seeing OpenGL-ES 3.1 devices and handsets beginning to ship. It means your phone is going to have compute shaders in its OpenGL GPU. And that's going to be, I think, the first API that's going to be pervasive. OpenGL-ES is already in every mobile device pretty well out there in the universe. And all of those devices over the next few years are going to get this compute shader capability. So, for many people, particularly if you're doing a graphics application already, you might be already using OpenGL-ES. It's easy now to add some vision processing perhaps with OpenGL-ES compute shaders. For many people, it's going to be an attractive, pervasive way to go. But you're programming GLSL, you're not programming in C, and you're limited to really GPU acceleration because OpenGL-ES is a GPU API, so it's not so applicable for running on a DSP. There aren't many DSPs out there that will be able to support OpenGL-ES. So that's kind of the compute. We have a lot of APIs out there, which is good. Different developers have different choices to do vision and image processing. We have this weird gap in the industry, though, is how do we actually generate a sequence of images out of the camera subsystem into the processors to have the right sequence of inputs that you can have a good application. So this is the purpose of the Khronos camera control API. It's so new, we're still debating on the name and the logo. But essentially, it gives you a lot of control over the camera subsystem, the sensor, the ISP, with a lot more depth and flexibility than pretty well any of the platform APIs that are out there right now. So we're thinking about how to approach depth sensors, sensor arrays, how you would synchronize the camera sensor with the other MEMS type sensors in a system, generating high frequency bursts of images from the sensor array with different properties. So you can start doing the vision processing that you need to do. The other key API is sensor fusion, because there are so many sensors out there. Mobile devices, I had 19 on my slide. I think it's 22 now sensors on the latest mobile devices. Apps really want to use all of the sensors on these mobile devices, but it's very specific on how to use many of these sensors. You have to be quite a sensor expert in many cases to really make best use of the sensors on mobile. So stream input is an API for sensor discoverability and sensor code portability. In essence, the apps can request from a list of semantics what they want. It can be as basic as getting the quaternion, the position of a device, and the device will figure out the best way of providing that information back to the application, or perhaps contextual information such as am I walking, running, driving, sitting. Again, the device will figure out the best way of delivering that information back to the application in a platform and OS portable way, and enable the sensor community, the hardware community, and the middleware community to innovate, to deliver the best power and quality of the sensor stream back to the developer. So this is a graph that we've been showing for a while, showing how all these different APIs can be used together in a typical augmented reality application. So let me quickly walk through this. So the camera control API will be controlling the camera subsystem. EGL doing two things, providing the timestamp information between the camera sensor and perhaps the MEMS sensors and any other sensors on a device, and also providing the streaming capability of the images from the camera down through into the rest of the system. OpenVX will be the way that you can provide performance portable vision acceleration, doing the extraction from the incoming imagery for your AR tracking, for example. Stream inputs will combine the sensor input from the MEMS sensors and the vision subsystem. You'd have an application doing application acceleration using OpenCL. Your rendering and composition would use OpenGLES. That's where you'd render the augmentations. OpenSLES is something I haven't mentioned, but it's a 3D positional audio API from Khronos. And driving your output. So we're getting close, because not all of these specs are released yet, but we can actually see where we're headed, and we can construct a complete AR subsystem that's not dependent on any particular platform and can be portable and totally based on open standards. I'm going to finish up because I'm almost out of time.
Could you also say about the 3D compression and transmission work?
Yeah, so I'm going to finish up with the web-based stuff because the two are becoming increasingly interrelated. This was an interesting study. This is numbers from the third quarter 2013. So you can't probably read it, but this is the mobile developer mindshare. This is essentially the developers developing for each of these platforms. This one is Android, not a big surprise. Android is the most pervasive mobile OS. The second one down is iOS, and that's not a surprise. iOS is a very stable and easy to develop for platform. This close third is HTML5. So now the developer community has really begun to latch onto the fact that you can, for the first time, use HTML5 to develop portable application code that can literally run across different OSs and devices. So bringing some of this capability from the native world, all of those APIs I've just been discussing as C or C++, bringing them up into JavaScript to make them available to the web community is one of the ways that we can really make AR applications portable, leveraging HTML5 and its momentum. So we've already started doing that. WebGL is a binding of into JavaScript of OpenGLES. WebCL is a JavaScript binding of the APIs in the OpenCL framework. So that will enable the web developers to distribute C kernels across available heterogeneous computing resources from JavaScript. We're working to bring path rendering extensions into OpenGL and OpenGLES. But then it leaves this interesting opportunity. These yellow blocks are not committed projects yet, but they're perhaps something that we should be thinking seriously about, bringing vision, acceleration, stream input for sensor fusion, camera control into the browser, starting from this firm foundation of native APIs that are proven and shipping by the Silicon community, could be an effective way of enabling the web community with this kind of functionality. And we're talking with W3C about that potential possibility. The last thing is, once you have things in the web, you need to transmit things to the client because typically, you're not going to have all your assets installed. The value of the web is things can be dynamically downloaded. So we're beginning to build on the COLLADA file format to build out the GLTF file format for OpenGL transmission format. And I think we're making good strides to making an ecosystem come together. So the way this comes together is that COLLADA is an importer-exporter format that you can now import-export assets from pretty well any of the authoring tools out there, 3D authoring tools. We now have a COLLADA to GLTF translator. GLTF is a file format that's been designed to need the minimum possible processing to just drop into a WebGL client. It's shovel-ready, because on a mobile device, if you're not careful, you spend a lot of time just doing boring file format translation from whatever your tool has just emitted to a native WebGL type format. GLTF is a great target. You can take a GLTF file and drop it into a WebGL client. It doesn't define any client behavior like VRML. It's agnostic to what your code is actually going to be doing in WebGL, but it does solve a lot of the file formatting issues. And of course, you can bring other file formats into GLTF. Khronos has funded a open source project as a 3.js GLTF importer. That's pretty well complete now. It's on GitHub. 3.js is the framework that most WebGL content on the web actually uses. We're beginning to find WebGL is now pervasive. Microsoft, amongst others, are shipping WebGL. Pretty well all the desktop browsers and increasingly all of the mobile browsers are close to shipping WebGL, which makes it interesting to create format content for WebGL. In fact, we're finding a lot of tools out there now actually using WebGL to create the tools themselves, and so you get this virtuous cycle. Then, as a result of this group, Khronos and MPEG have been working closely together to take some of the 3D royalty-free 3D compression technology that's available in an open source package called Open3DGC. And we've been using GLTF as a carrier for compressed payloads to see how much we can compress 3D assets as we transport them across the web for a WebGL client. And this is a few months old, but you get to see, this is the gzip baseline, and this is the data using the MPEG compression and GLTF. It's orders of magnitude smaller, and that's an ongoing project. If this is something that's of interest to you, please come and chat. We'd love to talk to you. So that's it. So we're building a bunch of stuff. We'd love your participation. We think it's relevant to AR. Tell us if it's not. Thanks.
Is this a good time to have questions, or should we?
It's up to you.
Neil.
Yep. Hey, Rob.
Yeah, so the camera control is awesome because that's the perfectly whole website.
Yeah.
Is that include introspection as well, or is because the name suggests more about the control?
Yeah. So, Michael, do you want to stand up? So we're privileged to have Michael Savigny here, who's the chair of the camera working group at Khronos. So, do you want to answer that, Michael?
So introspection. Yeah, so getting more detail.
Yes, that's a great question. And traditionally, every vendor has had to do their own thing. It's been very fragmented, and it's been very unreliable how much information you can extract from different platforms. There's actually the EGL working group. The EGL is kind of the glue that sticks everything else together. The EGL working group is actually now discussing to define a standard set of power and performance profiling hooks in the standard EGL API. So, defining a minimum of what will be available for trying to discern what's going on inside a system. And we're hopeful that if that gets adopted, that will make it much more easy to predictably find what's going on inside in a bunch of different systems. Yeah, so EGL is working on that. I don't have a timeline. It's not a trivial problem, which is why it's not been done before. But I would be hopeful in the next 18 months, 2 years perhaps, we'd have something.
But sooner if you get involved.
Yes, I mean, if people nag us, that tends to make it higher in the pile, yes.
Neil, do you know when the stream input will have its first version ready, and do you have the buy-in from the sensor people that you need?
So that's a great question, because we've restarted Stream Input, because Stream Input started out being everything you see today in OpenVX and the camera API was originally all bundled up in Stream Input, which made it, well, it's interesting because it spawned off VX and the camera. But now we've rebooted Stream Input as being just really for the MEMS sensors. And meanwhile, there's been other stuff out there which we take as proof positive that this really is a need. There's initiative by sensor platforms and ARM called Open Sensor Platforms. It's an open source project called OSP for short. And it has much of the same goals as Stream Input. And we actually think it's a good thing because the chair of Stream Input is sensor platforms. So we have the same kind of community driving both. And what I think is going to happen is that it'll be like OpenCV and OpenVX. It's good to have an open source initiative out there as we kind of figure out what to do. But in the end, we're going to need a defined API with conformance tests. And I think that's the role that Stream Input can play alongside OSP.
And the MIPI work, MIPI Alliance also has got some things that are relevant.
Yeah, yep.
You haven't told him when it's going to be available yet.
Well, Stream Input, we're aiming for a draft spec before the end of the year, before the end of 2014.